Okay, Chemistry 3101. This is Chapter 14, which deals with infrared spectroscopy in mass spectrometry. We're going to begin with infrared spectroscopy. Excuse me. And the whole point behind infrared spectroscopy is to be able to help us to identify functional groups. So make sure you know all of your functional groups, that you know what an ester, a carboxylic acid, a nitrile, an aldehyde, a ketone, an alkene, an alkyne, an alcohol, all those different things, an amine, an amide, etc. Make sure you know your functional groups very well, because that is the whole purpose of infrared spectroscopy, is to be able to identify functional groups. What we do is we run an infrared spectrum, is what we call it, on an organic compound, and we are able to differentiate between two compounds with two different functional groups by looking at their infrared spectrum many times. So let's get into it. And what is spectroscopy? Well, spectroscopy is just the interaction between matter and light. And you would remember studying light in general chemistry. You would have talked about the Bohr atom and how an electron could absorb a photon of light and get promoted from an n is equal to 1 to a higher energy level. In light, we also call it electromagnetic radiation. So we're talking about taking organic compounds, which are matter, and shining light on them, essentially, causing them to interact with electromagnetic radiation. Now, something that you want to know is that electromagnetic radiation is made up of two fields that oscillate in mutually perpendicular planes. We have an electric field and a magnetic field shown here. You see the direction of the propagation of the light beam. And something that you should know is that the difference, or the distance, I should say, between successive points on two waves, we call that the wavelength, or lambda. So lambda represents wavelength. And you would remember studying the electromagnetic spectrum in General Chemistry 1, and we're going to review that this morning. So wavelength. Anyhow, another thing you should know besides wavelength is that the number of waves that pass per unit of time, we call that the frequency. And for frequency, we use nu. So we use the variable nu for frequency. We'll put that here, frequency. And wavelength is usually measured in meters, or it could be nanometers, or even centimeters. And we'll get into that in a little bit. We'll put here meters or nanometers maybe. But frequency is measured in cycles per second. So we call that seconds to the -1. Or if you've studied physics, you would know that a reciprocal second is also known as a hertz. So those both mean the same thing, a reciprocal second and a hertz. Well, let's move on. It says that light can be thought of waves. We know that light has a wave-like component to it, but it also has a particle-like property. And we call those particles, or packets of light energy, we call them photons. So you would remember learning about the duality of light, that it has a particle nature and a wave nature. But you have to remember that the energy, or packets of light, are called photons. And it says here the energy of each photon is directly proportional to its frequency. So let's make sure we understand that if we have this formula here, energy is equal to h times nu, and nu is frequency, and h is Planck's constant, so h is equal to 6.626 times 10 to the power of -34 joules times seconds. Well, if energy is equal to Planck's constant times frequency, then we have energy is equal to joules times seconds multiplied by reciprocal seconds, and this cancels out, and we get our energy in joules, right? And we should know that joules are a unit of energy. So again, energy is directly proportional to frequency. So if we're talking about high frequency, we're talking about high energy. Whereas wavelength is inversely proportional to frequency. You might remember from general chemistry, you would have learned that the speed of light is equal to wavelength times frequency. Well, we can rearrange this formula and solve for frequency and get that frequency is equal to the speed of light over wavelength. Now we can take this formula and we can substitute the frequency into here. And what we end up with is this. We end up with energy is equal to h times constant times c, the speed of light, divided by wavelength, and we can see that energy is inversely proportional to wavelength. So let's write that over here. Energy is directly proportional to frequency, but it's inversely proportional to wavelength. If you've forgotten what the speed of light is, for this class, you can just use 3.00 times 10 to the power of 8 meters per second. So that's the speed of light. That's a constant that most students have memorized at this point in the game. All right, well, let's move on from there and let's review the electromagnetic spectrum. Again, this is something that you would have covered maybe in high school physics. You definitely would have covered it in General Chemistry 1, and everybody who's hearing the sound of my voice has passed General Chemistry 1. And so you should be aware of the electromagnetic spectrum and the different frequencies of electromagnetic radiation. You should understand that we start with microwaves or radio waves that have long wavelengths and have short frequencies. And then we get up to higher energy. So we get up to infrared, then near infrared, then visible. So this is what we can see with the naked eye. Then we get into UV, and then up to X-rays and gamma rays. And so what do we see? We see that as the frequency increases, the wavelength decreases, right? They're inversely proportional to each other. And another thing that we could add here is we could add a third red arrow and put another arrow this way and say energy, right? Because we know that as you go from microwaves up to visible rays, up to UV rays, up to X-rays and gamma rays, that the sources of electromagnetic radiation get stronger and stronger. They have higher energy. Now, what we're interested in this class is going to be infrared waves, because we're talking about infrared spectroscopy in chapter 14. And it says here that it goes all the way from 2 micrometers to 50 micrometers. And we're really only interested in going from about 2.5 to 25 micrometers. Now, if you convert that into centimeters, that would be around, so anywhere between 2.5 micrometers to 25 micrometers. Let's just write that down. So we're interested in 2.5 micrometers to 25 micrometers. That's the wavelengths of infrared light that we're going to be subjecting our compound to. So that would be, I'm just converting this in my head. So if you converted that into centimeters, and I'll tell you why, it's going to make sense why I'm converting it into centimeters later on, but that would be 2.5 times 10 to the negative 4 centimeters to 25 times 10 to the negative 4 centimeters. Now, if you've read the entire chapter before I come into class, you'll understand why we're talking about centimeters, but I'll get to that in a little bit. All right, so it says here that when light interacts with molecules, the effect depends on the wavelength of light used. And again, in this chapter, we're going to be talking about infrared spectroscopy. So this is our chapter 14 focus, at least for the first part of the chapter. But later on in chapter 15, we're going to be talking about how radio waves interact with matter, and that is the subject of nuclear magnetic resonance spectroscopy. And like I told you, when we're talking about infrared spectroscopy, we're talking about functional groups. That's the information we're going to get from an infrared spectrum. Is what are the functional groups present in this compound? Is it an aldehyde? Is it a carboxylic acid? However, in chapter 15, what we're going to get from NMR spectroscopy is the arrangement of all the carbon and hydrogen atoms in a compound. Now, at this point in the class, you've probably noticed that in organic chemistry, we talk about carbon atoms and hydrogen atoms a lot. They come up constantly in this class. And so in chapter 15, we talk about NMR, and we get the information as to how those carbons and hydrogen atoms are connected. Very, very powerful tool. We don't cover UV vis spectroscopy in Chemistry 3101, so don't worry about that. All right, well, let's get into it a little bit more here. It says that matter exhibits particle-like properties. On the macroscopic scale, matter appears to exhibit continuous behavior rather than quantum behavior. And if you're wondering, what does this mean exactly? Well, let's think about if we have a tire spinning on an axle, okay? If I asked you, I want you to make this tire spin at 25, miles per hour. I want you to make that tire spin at exactly 25 miles per hour. Well, your ability to cause that tire to spin at 25 miles per hour is only going to be limited by the precision of the accelerator and the instrument that's reading the speed. Okay, so you can definitely do that. But let's say I asked you, I want you to spin that tire at 25.2 miles per hour. Miles per hour. Could you do that? The answer is yes. Again, you would only be limited by the precision of the speedometer and the accelerator. So let's say you wanted to do something really wacky. You want to spin it at 25.23318 miles per hour. Now that's a little bit ridiculous. We don't, you couldn't imagine a police officer stopping you and saying, you were going 25.23318 miles per hour. No, maybe not. But could we do that? The answer is yes, because matter on the macroscopic scale, what we're used to in our everyday lives, exhibits continuous behavior, right? It exhibits continuous behavior. But what quantum behavior is something a little bit different. Quantum behavior is not intuitive to us because we don't see it as, or we don't think about it as much in our everyday lives. It does exist in our everyday lives, but quantum behavior would be something like this. If you were spinning the tire at 25 miles per hour, and then you could make it spin at 26 miles per hour. Then you could make it spin at 27 miles per hour, but you could not make it spin at any speed in between. Couldn't happen. That's quantum behavior. Now, if you're wondering, well, where would I see quantum behavior in my everyday life? Well, if you think about, just counting things, if you think about when a hen lays eggs, you don't say, oh, I went to the hen house and I got, 10.2 eggs. There's no, you get a defined number. You either get 10, 9, or 11, right? So that would be an example of quantum behavior in everyday life. We could come up with others, but that's neither here nor there. All right, now matter on the molecular scale, and this is what we are interested in organic chemistry. We're always talking about molecules this and molecules that. Well, molecules exhibit that quantum behavior. And it says that you can have a molecule rotating or vibrating, but it can only rotate or vibrate at certain energies. Now, before you get into what does vibration mean? Okay, vibration means the stretching of bonds for us in this class. Okay, in rotation, you can imagine what rotation means. It's just the molecule rotating in space. Now, unlike the tire, which we could cause to rotate at any speed we want, it's a little bit difficult to wrap your head around it, but a molecule can only stretch its bonds at certain frequencies, so it can only vibrate at certain frequencies, and it can only rotate at certain frequencies. Again, a bit of a brain bender. How is this possible, Mr. Dion? Well, it's quantum mechanics. It's a difficult subject, and we don't get into too much detail. You just have to take my word for it. That if we're talking about the vibration of a bond in a molecule, that it can vibrate at one energy level, then it can vibrate at the next energy level, then it can keep on going up to higher and higher energy vibrational states. However, you see this gap here where it says delta E? It cannot vibrate anywhere in here, here, or here. Those gaps are totally empty. Again, not intuitive, but it's the way it is. Now, you would have seen this with the Bohr atom. When you saw an electron be excited from one energy level to the next, you would say, okay, well, the electron can be excited from n is equal to 1 to n is equal to 2. Then it can relax from n is equal to 2 to n is equal to 1 and emit a photon of light. And you can measure the wavelength of that light and all that stuff. But the important thing is, when you learn this in general chemistry, that you would have understood that the electron doesn't exist in between two different energy levels. And this is the same treatment. This is the quantization of matter. Well, again, for the electrons in covalent bonds, the vibrational energy levels are separated by gaps. And again, this is what you would have learned with the Bohr atom. N is equal to 1, and then you went to n is equal to 2, then they get a little bit closer together. N is equal to 3, all the way up to all the way up to n is equal to infinity, when the electron is infinitely separated from the nucleus. Well, it says if a photon of light strikes a molecule with the exact amount of energy needed, then the light will be absorbed and a vibrational excitation will occur. So it's going to be excited. Okay. And infrared light can cause molecular vibration. And again, it says different types of bonds absorb different IR energies. And this is where it gets powerful. Because let's say we're comparing an alcohol Well, what kind of bond do you have in an alcohol? You have an oxygen-hydrogen bond, and let's say you're comparing it to an amine. Okay, here's an amine. Well, in an amine, you have a bond to hydrogen, but it's between nitrogen and hydrogen. Since these are different bonds, they absorb different IR energies, and we can plot that, and therefore we can distinguish between these two different types of bonds. Now, eventually, that energy that's absorbed gets released from the molecule as heat. So let's talk a little bit more about this whole thing of vibrations. And sometimes students will find the word vibrations a little bit annoying because they think, well, if I'm thinking about vibrations, I'm thinking about the Beach Boys and good vibrations, maybe. No, I'm kidding. But anyhow, if you're thinking about vibrations, you imagine you start your car, okay, and then if you were to put your hands on the hood of your car, if it's a gas-powered car, you can feel some vibrations from the engine, or your lawnmower. You grab the handle on a gas-powered lawnmower when you start it up, you can feel vibrations. Well, we're talking about that to some extent, but the main type of vibrations that we're actually interested in this class, you might not think of them as traditional vibrations, like a lawnmower, but we're actually talking about bonds stretching. So when we talk about bonds being able to stretch, and you can think of two atoms being hooked together by a spring, that would be like their bond. The bond can stretch and contract, okay? And that is a type of molecular vibration. Another type of molecular vibration is what we call scissoring. So you can imagine just like a pair of scissors. So if I was to draw a pair of scissors here, and Mr. Dion is not an artiste, but if I had a pair of scissors like this, you know that the scissors can close and open, and we call that a scissoring vibration. Didn't mean to do that. Okay, there we go. We can have a twisting vibration, so you can imagine it twisting back and forth. And later on, I'm going to open up a page on Wikipedia that will show you some of these stretching and bending vibrations. But again, we're mostly going to focus on stretching vibrations in Organic Chemistry 1. So mostly going to focus on stretching vibrations in this class. All right, let's move on from there. And I'm not going to get into the whole section on night vision goggles or thermal imaging. I'm just going to put this out there as an FYI. If you want to spend the time to read this in the textbook, go ahead, but it's not going to be covered on the quiz. So let's get into the more important things, at least the more important things for our class. It says here that the energy necessary to cause the vibration depends on the type of bond. Okay, so this is just me extrapolating on what I told you already. I said if you have two different bonds, they're going to absorb different frequencies of infrared light. Well, let's compare two different bonds. Let's compare a carbon-hydrogen bond with a carbon-oxygen bond. They're two different bonds, aren't they? Yeah, absolutely. Well, you see that the energy gap between the stretching frequencies for the carbon-hydrogen bond is bigger than that between the carbon-oxygen bond. Now, if you're a student, which I know you all are, you might be going, well, why is that? Why would they have different, energy gaps between their stretching frequencies? Well, we're going to get into that in detail in a few minutes. But again, I want you to understand that what happens is that you have your bond at some kind of lower stretching frequency, then it absorbs a photon of light with exactly this difference in energy, and then it's going to be promoted to a higher energy level. All right, that's the whole point here. We go from lower energy, so lower energy down here, up to higher energy by absorbing infrared light. Well, we're going to switch gears slightly here and just talk about what an infrared spectrometer looks like. And this is an infrared. Oops, didn't mean to do that. There we go. This is an infrared spectrometer shown down here at the bottom. Just if you're wondering, what does the instrument look like? Is it a mainframe? Does it take up an entire room or something like that? Does it have to be carried on the back of a flatbed truck? No, not at all. An infrared spectrometer is actually a pretty small instrument. We have a couple of them at UCCS. They're just sitting on the bench top in a lab. They're just, kind of permanent there. But all it is a little, box like this, and you can put your sample in you put your sample on the instrument, essentially on what's called a lens, and then it shines infrared light on the compound, and then you see the spectrum show up on a computer. It's not much more to it than that. But again, the frequencies of light that are absorbed tell us about the types of bonds and the functional groups that are present. Remember, this whole idea of energy, well, you saw a few minutes ago that energy was equal to Planck's constant times frequency. The energy is directly proportional to the frequency. So higher frequency, higher energy gap. Lower frequency, lower energy gap. Well, let's get back to this thing here. Now, how are the samples prepared? It says here that you could put them on a sodium chloride plate, or they can be made into a KBR pellet. I'll be honest with you, I haven't done that in years. The modern spectrometers are much better than the old ones where you had to prepare all these plates and things. Now you can just put the sample directly on the lens and then you clean it when you're done. But yeah, much simpler. All right. Well, if you're after all of this, of me rambling on about energies and frequencies and stretching and this and that, if you're wondering, well, what the heck does an infrared spectrum look like? I kind of saw one here, Mr. Dan. You kind of showed me here, but what does it really look like? Well, this is an infrared spectrum right here, and this is what you're going to have to be able to look at and determine the functional groups by looking at it. And I'm going to teach you how to do that. This is called an infrared absorption spectrum, and it plots the percent transmittance as a function of frequency. Now we have percent transmittance over here on the y-axis, but then you have, that's not frequency, that says wave number. If you're like, I thought you said it was frequency. This is wave number. Well, I'm going to get into the wave number with you for a second here, because it says that the wave number, excuse me, is in reciprocal centimeters. And I brought up the wavelength of light in reciprocal centimeters, in centimeters a few minutes ago. If you remember, I told you that the wavelengths of light that we're interested in this class is 2.5 times 10 to the negative 4 centimeters to 25 times 10 to the negative 4 centimeters. But you don't see wavelength down here, you see wave number. And this is a standard that we use throughout the scientific community. We always use wave numbers, and the wave numbers range from 4,000 reciprocal centimeters to 400 reciprocal centimeters. So let me just back up for a few minutes here, and we'll get into this whole wave number thing so that you can understand, where the heck does this come from? So I'm really backing up here, aren't I? All right, let's go down here and let's just take a look at the portion of the infrared light that we're going to irradiate the sample with is anywhere from 2.5 times 10 to the negative 4 to 25 to the negative 4 centimeters. So again, that is just 2.5 micrometers to 25 micrometers. So I've just converted the micrometers into centimeters. Okay, so where does wave number come from? Well, the first thing you need to know is that the symbol that we use for wave number, I'll scribble it down here, wave number, is this here. We use like a nu with a bar on top of it. That represents wave number. And wave number is equal to frequency over the speed of light. So frequency over the speed of light. But something that you would remember from earlier on is that we said that the speed of light was equal to wavelength times frequency. So that means that frequency is equal to c over wavelength. Well, now if we take this definition of frequency and we plug it into this formula here for wave number, look what we get. We get that wave number is equal to c over wavelength times c. So what happens is that c cancels out and we get that wave number, the wave number is equal to the reciprocal of the wavelength. Now you see why I put the units of the wavelengths in centimeters. Let's just try one here. If we take 1 divided by 2.5 times 10 to the negative 4 centimeters, we end up getting 4,000 reciprocal centimeters, or centimeters to the minus 1. I'm kind of running out of space here, but if you do 1 over 25 times 10 to the negative 4 centimeters, then you end up getting 400 reciprocal centimeters. So what do we see? We see the shorter wavelength, higher frequency, higher energy is going to be at the far left of the spectrum. So let's go back here. So this is higher wave number, higher frequency, higher energy, right? This is also shorter wavelength, which we saw was for 4,000, it was 2.5 times 10 to the negative 4 centimeters. When you go to 400 reciprocal centimeters, this is lower wave number, obviously. It's also lower frequency, lower energy, and this is where we have a long wavelength of 225 times 10 to the negative 4 centimeters. But again, everybody uses wave numbers. It's a convention that we use across the scientific community. So if you Google infrared spectrum, or if you look up a video on infrared spectroscopy on the internet, it's always going to have wave numbers on the x-axis. So now you know where wave number comes from, and now you kind of know what it represents. Well, let's get back to this whole idea of transmittance. Well, what does transmittance mean? If I was to say the light transmitted through the sample, it would mean the light passed through the sample, right? So if the transmittance goes from 0 to 100%, if I had 100% transmittance, that would mean that up here on this line, that means that all the light just went through the sample, right? So if you go up here, you know, everything that's between these two lines, pretty much the light just went through the sample. So what are we interested in? We're interested in the parts where the light was absorbed, and we call these absorption bands. You can see some light was absorbed here at about 3,400 reciprocal centimeters. There was some light absorbed here around 3,000 and a little bit below 3,000. There was some more light absorbed here, and we call those absorption bands because those peaks, if you will, represent where the infrared light was absorbed by the sample. And that's what we're interested in. We're interested in the sample absorbing infrared electromagnetic radiation. Give me a thumbs up if you're with me so far. I've covered a lot of the theory already. Kind of interesting, you know, maybe a little dry, but manageable, okay? So this is just a slide that I posted where it talks a little bit more about the wave number. And of course, I showed you how to take this to say that wave number is equal to frequency over the speed of light, to being wave number is essentially equal to nothing more than 1 over the wavelength. So there we go. We've covered that. Let's talk about these absorption signals, or these absorption bands, or these peaks a little bit more. You know, you can see that they all have kind of a different shape to them. This one here is kind of broad. This one here is kind of pointy. We'd say that's sharp. And so not only are we interested in the particular wave number of an absorbance, we're also interested in its intensity, how much it is being absorbed. You can see that some things absorb a ton of light, some things absorb next to nothing, and then some things are kind of like in the middle of the road. And the other thing that we're interested in is the shape, right? Some of these peaks are really broad, others are really sharp. Why is that? Well, we're going to get into all three of those things: wave number, intensity, and shape, because there's information that can be garnered from all of these things. Well, let's take a look at wave number.